So let's talk about Grignards. So Grignards are, I mentioned a little earlier, going to have the same mechanism as the acyl nucleophilic substitution and acyl nucleophilic addition. It just depends on the type of carbonyl that we use. So Grignard reactions were actually discovered um, as a way of adding carbon. So this is actually one of our second ways that we can make carbon-carbon bonds, but specifically we're going to make a carbon-carbon bond that has an alcohol on it. So it takes these organomagnesium compounds, which you make. You usually don't buy it, you usually make it. Some of them you can purchase, but they're very reactive, so they're usually not very, they don't stick around very long. But you can react them with ketones and aldehydes to make different kinds of alcohols. So carboxylic acids, um, some of their derivatives of carboxylic acids can also work, and we'll talk about that, especially more in a future chapter, but we'll talk about that. These reagents are actually water sensitive. So how do you get a Grignard reagent? So a Grignard reagent is basically taking a organohalide, so some sort of halide, plus magnesium metal, and you heat it up, usually in a solvent like diethyl ether, something that's aprotic. So you need an aprotic solvent. And I'll tell you just in a second why you have to use an aprotic solvent. And it basically inserts the magnesium between the carbon group and the halide. So why you want this to be aprotic? Because this is actually a strong, like it's a really strong nucleophile. It's also a very strong base. And so if you use something protic, it will actually do an acid-base reaction. So that's not actually good. So like I mentioned before, first you make the Grignards. Sometimes you can buy them. Very few I've actually been able to find. And even then, they're so reactive that they come in these weird containers to protect them from fire and, from causing fire, not from them catching on fire, but them causing fires and all sorts of things. And so the insert itself. And so what's important here is that carbon is really going to behave kind of like a carbanion, because carbon next to any metal is going to be more electronegative. So the carbon group will act like a carbanion. And so your textbook shows it kind of like that, but it's in reality this is a coordinate covalent bond, so it is not an ionic bond, it's more coordinate covalent. And so this carbon attached to the magnesium is going to act as a um, kind of like a carbon ion. So it's going to be your nucleophilic component of the molecule. You can use the halide as bromines or chlorines. We often don't use fluorines or iodines because fluorine tends to be way more reactive. Iodine tends to be really unreactive in certain circumstances, and so it's usually chlorine or bromine. So, like I mentioned before, because the organo magnesium reagent is extremely, extremely basic, it's going to react with things like water and alcohols and deprotonate them. And so we have to use aprotic solvent. So the most common example of an aprotic solvent is diethyl ether. People also use THF as some examples. So THF, so diethyl ether here. THF is in a ring. These are very common solvents that people oftentimes use. What I have here is an example from the literature of a molecule that utilizes the Grignard reaction to do its work. And remember I said that the Grignard can act like a nucleophile, and it can act like a base. So here it actually acted as a base. It deprotonates this OH group, and then it can do some other reactions that we see later on. But because of its basicity, it actually is used as a base in this case. And this was used to make a molecule that had anti-HIV activity. It's not the only step, but it was one of the steps in this mechanism. So just like you saw with the acyl nucleophilic additions and substitutions with the reducing agents, the mechanism is the same here. So wherever I use nucleophile in those mechanisms, you're using the carbon-base group as nucleophile, and I'm going to draw each one of those. So when you have your reactions, just be careful that on your molecule you don't have incompatible functional groups. So you don't want other functional groups other than the um, the ketones and stuff like that that will react with the Grignard but not stop the Grignard. So alcohols are actually not good things. So if I had something like this and I had an alcohol, this would be a poor choice of a starting material, and I will use SM for starting material. As we saw before with the lithium aluminum hydride, how it reacts twice, Grignards do the same thing with esters. They will react twice. So let's draw the mechanisms. So I'm going to use generically an acetone molecule again for my ketone. So I'm going to draw here a Grignard reaction. That's an acyl nucleophilic addition, and then we'll do the acyl nucleophilic substitution with the ester. So the electrons come from the bond to the carbonyl, breaks the double bond, and you add your R group, which is always some sort of carbon group, by the way. It's not a hydrogen ever. Then because this is unstable, it's just going to sit around until you get an acid to protonate it. So if you start with a ketone where, let's say these two R groups, I'm going to call this R1, R2, and you react it with a Grignard, I'm going to call this R3. You're going to end up, when you're done, adding an R group here and a hydrogen here. So your product is going to end up being something like this. Okay. So if we start with a ketone where R1 and R2 are carbon-based groups, and I'm going to just use an asterisk C to represent anything, any kind of carbon, we're going to end up with a tertiary alcohol. If, for instance, your R1 is some sort of carbon group, but your R2, your group is some kind of aldehyde, and you have something like this, you're going to add R3 here, a hydrogen here, and since the Grignard, you're adding a carbon-based group, you're going to end up with a secondary alcohol. And the last thing is, if you start with formaldehyde, where it's just hydrogens, you're going to add your carbon-based group here, a hydrogen here. You're going to always end up with a primary alcohol. So this is another way that you can come up with primary, secondary, or tertiary alcohols. But you'll never get methanol because methanol has no carbon. So this always adds carbons. So now let's do the mechanism for the ester. And it's just like the LAH. So I'm just going to run through it very quickly. The electrons come from the pi bond, opens up the carbonyl. Again, you have your OR group, which is a decent leaving group. Before you can protonate, it will get kicked off just like you saw with LAH. Now you got a carbonyl and a Grignard, just like we just did. Grignards react with ketones, so it's not going to stop. So for these, we end up adding 2 R groups. So you're going to end up with a tertiary alcohol when we're done. So you protonate next. Because nothing's going to happen at this point, everything is done. You can protonate and make your tertiary alcohol. Okay, so when we do these kinds of mechanisms, you're going to react twice, just like with LAH, because this is the acyl nucleophilic substitution. We can also do these reactions with carbon dioxide, and so try this one. Remember, this is partially positive. And so if you react that, you're going to end up with a carboxylic acid. So try that mechanism. All right, so let's try that mechanism out. Let's use some sort of Grignard. So I'm just using a generic Grignard. When you have specific problems, you need to know what the R group is, etc. And we have CO2. That's going to come and attack this. Open this up. So we added an R group. And so the next thing to do is just protonate. So this brings up 2 points. So other than protic solvents being bad for these reactions, another thing is carbon dioxide can react with these reagents. So if you don't want the carbon dioxide, if that's not your intention, you also want to keep carbon dioxide out.